There we go. Now my overlay's working.
Hey, you got one of those.
Would you leave that stuff alone? Tyler, you can sit. There's not going to be anything on my screen for a while yet.
Sitting is kind of...
Most.
I don't like to sit.
I know.
Me,
and you're welcome to...
the class. Stand up.
Well, you're welcome to stand up and move around if you have to. So, today we're talking about a lot of stuff, but a lot of what it is talking. It's going to be hard to hear me at times over the grating sound of metal on metal from the other room. It wasn't too bad. They're going to be almost done here cutting.
That's what you think. Those angles are bad. Like that machine does not do a 45.
Yeah, it's because you're cutting aluminum.
Huh?
You're cutting aluminum with a non-aluminum blade.
No, well, aluminum melting inside the blade, so you have to like poke it out once you're done.
If you guys had a diamond tip blade, it wouldn't be doing.
No, Brad, you want to go spend $300 on a diamond?
No, I don't. So, like I said, we're going to be talking about a lot today, so I want to get as much done as I can. We will be pausing every once in a while, simply because the longer I talk, the faster my mouth dries out. I take 3 or 4 medications a day and don't drink enough water to begin with, so after talking for about 30, 45 minutes or so, I have to stop and take a breather and, re-moisten my mouth.
Dude, why am I here?
You're here because...
No, I thought that we were doing one thing each.
What are you smoking? If you are going to be one of the programmers on this team, this is stuff you have to know.
Okay.
This is part of the programming training now.
I thought you said it was electrical.
Yes, but the concepts from the electrical stuff, the basic concepts of everything that is electronic has to do with your programming. If you guys ever want to use sensors, you've got to understand this stuff. So you've got to pay attention. Obviously this year, because of how constrained for time we are, we're probably not going to do anything super extravagant. But, hopefully, wow, it is picking up on the saw a little bit. Hopefully, this will give you a stepping stone for when we actually have the time to sit down and talk about what we can actually do with some of these sensors. Granted, we're not starting off immediately with sensors because we have to talk about some things and how sensors communicate with other things before we can do that. This will actually be a useful video for anybody that joins the team that wants to learn electronics or programming. Now, most of this is going to be me reading verbatim the notes that I made for myself over the summer. I'll be adding little bits and pieces in, so I'll be looking up at you once I'm done reading, just so that you know when I'm saying something or when I'm reading something off the page. So the first thing that we're going to be talking about is RoboRios. Now, obviously, you both know, and anybody watching this probably knows what a RoboRio is generalistically. It's the brain of the robot. I gotta stop using that word. It's not actually a word. It's supposed to be generally, not generalistically. I don't know why I keep saying that. I've said it for like the past 2 years, and honestly, it's getting a bit ridiculous. But anyways, the RoboRio originally was designed to sort of better fit the bill of what FRC teams need in order to do what we do. Originally what we used was something called the NI-C-RIO, or Compact Reconfigurable Input-Output Device. It's normally used in industrial applications like conveyor belts, automated processing systems, automated manufacturing. It's for things bigger than what we do. And while it's an extremely powerful tool, and it did what it did very well, it was not very extensible, and it had its own share of problems, particularly its form factor. The thing was huge. And to even use it the way we needed to use it, we actually had to have 2 boards. The brain of the computer itself, the C-RIO, and something called the digital sidecar, a little blue box that broke out all the digital connections, including all the connections for our motor controllers. It basically used up probably about 2 times the space as the Robo Rio does now.
They use like those big printer cables.
Yeah. So another thing about the Robo Rio is it was designed to be a little bit more robust than the C-Rio. The C-Rio wasn't real. Once the C-Rio was somewhere, it wasn't really designed to be moved around and changed. And once it was somewhere, it might get worked on once or twice in its life, but normally it just stayed there. You know, it might have its code changed. It might, you know, be shifted from one part of a cabinet to another, but it wasn't being taken off one robot, put in another, moved around by students, dropped on the floor.
It's pretty much what you're saying. If the C-Rio was still in effect, we would have had Robot 6 last year.
No, not necessarily. They were a little bit more robust than that because they were made out of metal. But still,
I'm sure
they did not take beatings as well as
When Brock kicks you, you know.
right.
I'm
They
sure
didn't
they're
take
going over a round
beatings
ball.
as well as the Robo Rios do now. The Robo Rios are actually designed to take some pretty serious shock. They are partially sealed, which means that if you could seal off the pin headers somehow and all the extra ports, you could probably actually make it waterproof.
Buddy.
Yeah, no. It would be a lot of work to make it waterproof.
You get big pulled in.
But basically, that's the very very general difference of the Robo Rio to the C-Rio. Obviously, the Robo Rio is faster. It's got more memory, both working memory and storage memory.
Is that because it's newer?
Right. And we're going to go into some other topic here in a minute about one very special change about the Robo Rio that's very different from the C-Rio. But basically, the Robo Rio is a more powerful, more compact version of the C-Rio. It's designed to be better and do what it needs to do in a smaller amount of space. Now, the Robo Rio varies very differently from the C-Rio in software. The C-Rio ran a custom operating system made by NI that nobody but somebody from NI had access to, which is one of the reasons why the C-Rio wasn't exceptionally extensible, because it ran this custom operating system. A lot of people didn't know a whole lot about it, and the basic stuff that you could do with it didn't really get you very far, which is why the people at WPI had to write libraries for us so that we could actually do what we needed to do. WPI in combination with NI. Now, when I say NI, I mean National Instruments, if you don't already know. Just want to make sure that you guys... No, that's Texas Instruments.
Oh, what's the difference?
They're two different companies.
Well, yeah, but they make...
National Instruments is Industrial Automation and Design. Texas Instruments
Okay, they're the ones that
is...
make your stealth bombers.
Texas Instruments, it makes ICs and calculators.
Oh.
So, like, the stuff that makes up the Robo Rio, there's probably some Texas Instruments stuff inside it. But NI is what brings all the pieces together to make it work.
You know how a stealth bomber works? They fly like this.
Yeah, I know.
It's not stealth bomber class.
Anyways, the Robo Rio runs on something that Tyler is actually partially familiar with now. The Robo Rio runs on Linux, which is the same operating system that Azazel has on it.
Oh, yeah.
What are you laughing at?
Name off your computer.
Oh, bite me.
Yeah, it was like Zazel. Was that like a brand?
No.
It's not a brand.
Linux is an open source operating system. Anybody can download the source code for Linux and do whatever the hell they want to it. They want to contribute to the project? Fine, great. They want to take the project apart and see how they can break it? Fine, great. They want to take the project apart to see how they can hack it? Fine, great. It's an open source operating system designed to be built upon so that you can add more functionality to suit your needs. Because of how versatile Linux is, basically all that's running on the Robo Rio is a dumbed down version of Linux. It doesn't have the graphical capabilities as most Linux distributions have. It doesn't have some of the commands and stuff that some Linux distributions have. But it does have the capacity to communicate with all the hardware on the RoboRio and facilitate the communication between all the devices that a robot needs to do its job. Which we'll be getting a little bit more into that later. Now, one thing that both the RoboRio and the C-Rio have that I want to point out that's a little bit different from your standard computer is something called an FPGA. Now, that's not something I came up with. It's not supposed to be a funny name. It actually stands for something. It stands for Field Programmable Gate Array. Basically, it's a collection of circuits that you program. When you program them and flash a chip, that chip behaves as though it is that circuit. It's a very powerful way of programming hardware. Conventionally, most people think of programming as software, but it is possible to program hardware using an FPGA. Now, the FPGA on the RoboRio manages things like timers and digital I/O and making sure that everything on the robot is accurate and properly being done in the proper order. And it takes some of the load strain off of the processor and makes sure that it doesn't have to do everything.
Oh, yeah. So faster.
So it's a little bit faster. Because the RoboRio in of itself, Justin's computer, his little crappy netbook, probably has a core processor clock of 2 gigahertz. 2.4 single core.
I don't know what a gigahertz is.
A gigahertz is, so a hertz is 1 on-off cycle.
Oh.
So a gigahertz is 1 billion on-off cycles in a second.
That's a lot.
Right. So
2.4.
So Justin's computer can do 2.4 billion cycles in a second. Now that's not necessarily 2.4 billion instructions, but it is 2.4 billion clock cycles, meaning that the clock is turned on and off to indicate that something new needs to happen during that clock cycle. Okay? Now, the RoboRio has a dual-core 667 megahertz processor in it, which technically means that that processor is slower than Justin's netbook.
Holy smokes.
So having the FPGA there to help out when the grunt work gets hard is helpful, because if the RoboRio had to do everything, it wouldn't work well. The C-Rio was much worse. The C-Rio had a 400 megahertz processor, and it was single core.
How many megahertz does that have?
Justin, where exactly are you going? Come on. Okay, there we go. We're back. All right, so we just got done talking generally about FPGAs and the speed of computers and blah, 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 blah. The other thing about RoboRios that's really nice is normally when FRC originally started with 3 languages, at least when it came to where C-Rios were concerned. Those languages were Java, C++, and LabVIEW. Now, they all have their strengths and weaknesses. And before I get into this, one thing that I wanted to talk about the new operating system that's on the RoboRio when compared to the C-Rio, is I want to talk about the language a little bit more generally first. Java is actually, personally, in my opinion, the easiest language for a team to learn. This team actually started with LabVIEW, which personally I think was a mistake.
Yes.
But we'll get to that reason why here in a minute. Java makes it very simple to get your robot to move in very few lines of code. I think Justin had probably a 12-file LabVIEW program, and in 5 minutes I had 20 lines of code that could do the exact same thing.
It wasn't even 20. It was like 10,
It was 18.
15.
So Java is very powerful in that it's very easy to get started with, and it's very easy to make, at the very least, simple actions happen without too much effort. the big issue with Java is Java has a lot of overhead, meaning that it takes a lot more processing time to do simple stuff, and it takes a lot more memory, that is working memory, to do simple stuff. And in some situations, depending on what you're doing on the RoboRio, if you're doing too much stuff in Java all at once, you can actually run out of memory. The other day I was working on my LED library, and I had a memory leak in my program, and I leaked out all of my RoboRio's memory and filled up all the space, and my RoboRio crashed. And I was like, what's going on? Why did all the lights go out all of a sudden? And then my RoboRio came back on, and it was like, recovered from a crash. Insufficient memory exception. I'm like, oh, oops.
Wait, what you put into it? Like,
I'm writing a library to control LEDs directly from the RoboRio. And I made a mistake and forgot to clean up some of the memory that I was using, and ultimately used up all the memory space in the RoboRio.
was like repeating?
Yeah.
Oh, okay.
I just wasn't. I was using stuff, and then I wasn't telling it to clear. Like, the RoboRio still thought it was necessary to keep around rather than get rid of it. So there was just a whole bunch of junk data stored in memory that wasn't being used for anything, and then all of a sudden, crash!
Robert.
No. Pay attention. I don't care. I don't care.
Okay.
C++ is the next language. It's probably the second easiest to learn. And it's very, very similar to Java. Albeit C++ does take away quite a bit of the memory overhead that Java introduces. But this comes at a cost. The reason why I don't like to teach C++ to new teams is because the reason why the memory overhead goes down is because the programmer is in charge of creating, managing, and freeing almost all of the memory in a C++ program. Whereas Java, you almost never have to deal with it, at least when it comes to robot programming. Now, is it necessarily hard? No. But it does take a certain level of understanding of how memory is referenced on a computer. And for some newer programmers, that concept can go a little bit over their head. So rather than trying to force that on them, it's just as easy to talk about Java and deal with the memory overhead issues, because most new programmers aren't going to be doing anything that's going to make them hit that memory wall. Albeit, Justin did find a way to do it with LabVIEW, and LabVIEW is the next question that we're going to be talking about.
Wait, I hit the memory thing?
You did. Remember when you were constantly recreating the same instance of a compressor?
Yeah.
Did you make a loop?
Right.
Yeah, it didn't like that.
So LabVIEW is the last language that is approved for specific FRC use. And LabVIEW is the only visual language, that is dragging and dropping blocks and connecting them together with wires, that you can use to program the robot with. Now, LabVIEW is designed for very complex automation, where a lot of things need to be happening all at once, and you need to have a very high-level understanding of something called abstraction. The idea that you don't necessarily need to know how something is done, you only need to know what inputs need to go in to get certain outputs.
I hate that. I want to know how something works.
And LabVIEW is one of those things where you have to put in inputs and pray that whatever comes out is what you wanted. Now, Java and C++ also do the same thing, but to somewhat of a lesser extent.
Or when you do something wrong, it says you did this wrong. In LabVIEW, it's just like, oh, it's all good.
The other thing about LabVIEw,
Just kidding.
is LabVIEW is very modular. It's designed to be broken up into many, many small pieces. And while good programming is very modular, even in languages that are text-based, for a new programmer, starting out immediately with modular programming is extremely difficult. because it's very, very hard for them to see how all the pieces of a program come together. Even for me, when I go and look at like Team 254's code, they always have extremely extravagant Java programs running on their robot. It takes me a good week to look through all their stuff and be like, okay,
Who's 254?
the cheesy poofs.
Wait, what do we? Is 254? Wait, what's the Gearhead one?
No, I can't remember.
Where are they?
That'd be a question for Trevor.
Where are they from?
I don't remember. That'd be a question for Trevor.
Why do you look at their code?
Because their code is interesting and cool. Because it
Oh,
does
I
all
thought
kinds of
they-
stuff
I thought you
in a
were,
very interesting way.
I thought you were like assigned to their team.
No, they don't need me. They do stuff that's beyond me at times.
It's gonna be like, how many teams do you have?
Wait, how many people are as good as you?
None.
Quite a few.
Perhaps not. Special, like RoboCop.
Anyways,
Okay, Bert and Ernie.
Justin's issue was that he didn't probably understand the concept of the abstraction that went on, and he was repeatedly creating the same representations of the same motor controllers and his compressor object over and over and over again until the memory on his RoboReo filled up and it crashed.
Didn't like that.
But the one thing that's really nice about LabVIEW is it's very easy to get data out of a LabVIEW program in neat and organized graphs. It's extremely powerful when it comes to things like that. And it's part of the reason why organizations like NASA use it.
They use LabVIEw?
Yep.
Really?
Oh, I thought that LabVIEw was just this little, like,
Yeah, I thought it was
FRC.
No, LabVIEW is its own true language. There are even, when we get to talking about Arduinos, there are Arduinos that can be programmed with LabVIEw. Or Arduino-like devices, I should say. But anyways, one other comment that I'd like to make is that because with the C-Rio, you were limited to 3 languages, period, end of story. Because it meant that the people that were working with NI to write the languages that we were using had to be working with NI to write them. There were some people that were working on some smaller project, but they never really panned out anywhere. Now that the RoboReo runs on Linux, you can basically program the robot in any language, provided that you have the right know-how and skill to communicate with the right things. And this is an extremely cool thing about the RoboReo, because in years to come, we may be allowed to use other languages like Python or
Would you wanna do?
JavaScript. Well,
Wait, what's the difference? JavaScript.
JavaScript and Java, they're very, very different. I know that they sound very similar, but they are very, very different.
That explains a lot.
JavaScript is normally used on web pages.
Yeah, I'd be looking into the info. Like, how do I mess with this? Because without saving it.
You go on the developer.
Huh?
You can't save it. Like,
Yeah, no, you don't save it. That's I've realized that. I was like, went on down some page and like type a joke and didn't save it. Dang it.
Anyways, in fact, there is one project going on right now that I know of that is actively maintaining and working on translating the WPI libraries into libraries that can be used with Python in the RoboReo. And it actually works quite well. Granted, Python is a little bit... If I were to put Python in our list of 3, Python is probably right about the same level as C++, but for different reasons. Python does memory management for you, but the language is loosely typed, meaning that variable names don't start with a type declaration. Like it doesn't say int, double,
Why not?
string.
So you can just use any.
You can just put anything in any variable, whatever you want.
Then
So that sounds pretty easy then.
so you just put.
Oh, but then you run into problems.
Yeah. you
What
know.
happens when you try to divide a string by 5? How do you handle that? And that's where the complexity comes in. But Python is right about on the same level in C++ in my mind. Python was about as hard for me to learn as C++ was.
Don't they like do games?
Only-
and
Doesn't it take you like 3 full months to learn a program?
For me, no. Once you learn the syntax of one language, then all you're learning is syntax in every other
It took
one.
you 2 hours, I guess.
So not 2 hours, but a couple of
YouTube video.
weeks worth of time, and I'm usually knowledgeable enough to know where I need to go next, which is to look for the libraries that I need to do what I want to do. And that's not working like for 2 weeks every day straight, like all day every day. That's like an hour or two a day.
What about 20 hours?
Now, one thing about LabVIEW is with LabVIEW there are ways to communicate with the lower level hardware on the RoboRio. Specifically the FPGA and something called direct memory access. We won't talk about that. It's not really useful to us. Getting access to it in Java and C++ is possible, but it's not easy. And really, most teams, there is and always will be an exception to everything. Most teams do not have any reason to use that facet of the RoboRio, albeit LabVIEW does break it out a lot nicer than Java and C++ do. So now we're moving on to our next topic, which for the previous topic and the next 2 topics, we're actually all under the same subtopic, which is RoboRios, Arduinos, and piggyback devices. And the next thing that we're going to talk about is Arduinos. Now, I have a very large bag that Justin keeps groping that has all kinds of stuff in it. Specifically, what I want to show you right now is Arduinos, which I have 4 of, I think, with me. Yep.
It's one of those other weird things.
Tell you in a minute. So.
You got a raspberry in there?
Hush.
Do you?
So, Arduinos are sort of like hyper-simplified versions of RoboRios. They are significantly less powerful. So if you remember, I told you that the RoboRio had a dual-core 667 MHz processor with an FPGA. Your average Arduino, there are other ones, but your average Arduino only has a 16 MHz processor and no FPGA.
Oh, I bought
That's sad.
those.
Sad thing.
But there's a lot of stuff that the RoboRio can do that I can do the same thing with an Arduino.
Like tell something to drive.
Right.
Well, I bought like control that has an Arduino.
How much do those cost? Like $20?
This one and this one were $25 a piece. This one right here is $30, and then this one right here is about $60.
Have you heard of the $9 computer?
Yes.
Is that good or bad?
It's not bad, it's not good. It depends on what you're using it for. And we'll get into that a little bit when we talk about piggyback devices. Now, Arduinos are really good for doing things that are repeated tasks that could be taken off the RoboRio's workload, like driving LEDs. Arduinos are extremely excellent at driving LEDs because you have a huge amount of control over what the processor is doing. The other thing that Arduinos are good at is taking in sensor data. Granted, you can't take in a lot of sensor data because you have a limited number of pins when compared to a RoboRio, but there are other versions that have more pins. This one in particular right here is
Selling for $5.99 at your local supermarket.
this is an Arduino Do, which is actually based off an ARM processor, which is in what is in most of your phones, except Justin, because he's had his phone taken away.
I get it. You don't need to rub it.
This actually runs at 84 megahertz. And this one right here is actually quite a bit faster because it actually runs on an Intel processor, which is the same thing that Justin has in his computer, albeit this one probably runs quite a bit better than the one that's in Justin's computer.
This computer's like, I don't give that thing like
So
that.
listen, you drop that like 6 times, you slam it on the ground, you put it in the computer, that's my computer for you.
Now, for the like I just said, for the most part, Arduinos run on chips called Atmel chips, just a particular company, with a particular instruction set and a particular way that they design their processors. Albeit some do run on ARM processors, like the Arduino do.
Did you say not to get an ARM processor computer?
A what?
Like one of those computers, because they stink?
What do you mean? An ARM computer?
Yeah. Right.
They don't stink. They work for particular purposes. No computer necessarily stinks. Like if your computer was not running, what is it running? Vista 7?
Yeah.
If your computer was running XP, it would run fine. But somebody, I wanted to say one word, but I'm not going to. Somebody jammed, as opposed to the other thing that I was thinking. Somebody jammed 7
I did that.
onto that computer.
No, they gave us this little USB, and they said, so you plugged in, then you go like into before it starts up, you like press F7 or something, then you go.
Did you flash that computer with the stupid driver's station image?
Yeah.
Why?
Because it said in the instructions to
You
do
don't
that.
have to. You can just download. Oh,
Well, I didn't know.
Lord. Anyways, ARM processors had their own strengths and their own weaknesses. My phone is about 4 times faster than Justin's laptop.
That's not hard to beat. Stop rubbing that in my face, too.
Well, okay, in comparison, my phone is about a sixth the speed of my laptop.
What about a gaming computer?
That is a gaming computer.
It's a game
Like,
computer.
You see number 1 in gaming?
I didn't see that. I still don't see it.
It's on his...
Sticker.
Like,
Anyways,
I've seen gaming computers.
granted, there are things that change how much power a processor has other than just clock speed, but we won't get into that. But generalistically speaking, said it again.
What?
Generalistically.
Dude, just submit it to a dictionary and...
Anyways, let's move on.
Generalistically.
Yeah, that's right.
Now,
20 times.
Arduinos also have most of the same hardware connections as a RoboRio. Your basic Arduino has PWM, like what we use for motor controllers.
Scale up 2.
It has, it has 1, 2, 3, 4, 5 standard. It also has analog and digital I/O. It has I2C and SPI, which we'll be talking about later. And on some Arduinos, particularly more powerful ones, it can also have a CAN interface and digital to analog converters or analog to digital converters built in. Digital to analog converters. Blech. Sorry, brain fart. Digital to analog converters just take a digital signal and convert it into a true analog signal rather than doing some funny business with turning the digital I/O on and off real fast to try to create a synthetic voltage. Which we'll talk about in a little bit.
I'm gonna make Tesla coil.
Tesla kid.
Start with a Van de Graaff generator. That's a little bit safer.
Yeah, I want to like do stuff like that, but I don't want to kill myself, so
Van de Graaff generators are pretty safe. Now, the next thing that we're going to be talking about,
That's a raspberry.
one thing that Arduinos are really good at is extending their capabilities. Particularly because they all have the same basic form factor, or pinout. These are all shields that provide the Arduino platform calls them shields, to provide different functionality to an Arduino based to suit its needs. Shields are stackable. You can stack as many as you want as long as you have enough pins to communicate with them all. Depending on what you need, shields can do a variety of different things. This shield right here was actually in my LED hat project for years. It is a Bluetooth shield.
Bluetooth.
It has basic Bluetooth support so that I can communicate with my phone and send instructions to whatever I
What
want.
phone do you have?
Yeah, like you have like.
LG Nexus 5X.
Obviously not an iPhone.
No, because iPhones are meh.
Oh man.
Meh.
You can't program those.
Oh, I can. Just they don't have as much gumption.
Gumption.
And it's a very closed source, and that
Closed
bothers me.
source.
This is an SD card shield, like what you'd standard see in like cameras and
My taco.
computers.
Wait, what's the other side? That's a big one.
Yeah, it's double-sided, which is a little bit broken, but okay.
Yeah.
I don't hardly ever use it.
It's broken.
This is an Ethernet shield. I can communicate with regular networks using this.
So you can like plug it into your.
Wait, can you program something to learn?
Not with an Arduino.
Well, yeah, is it possible?
Yes,
Look
you
at
can.
Furbies.
I mean, in terms of AI, yes, there is artificially intelligent computers that have been learning.
That's good. So
Have you ever done Cleverbot before?
No.
Huh? Is that,
Next-
is that like the little thing on here?
No. The next opportunity that you get, go to Google and look up Cleverbot and have a conversation with Cleverbot. The last time I checked, Cleverbot was 42% human, where you could hold a conversation with it and it would be roughly correct 42% of the time.
That's a lot. You serious?
Yeah, I'm serious.
That's,
And this was a couple of years ago.
Oh.
The project might be closed, or it might be even better now. I don't know. And then this shield right here, this shield's a little bit dated. It uses a very old IC to do this, but this is a motor controller shield.
It sounds like they're playing some weird music, but they.
I've actually never used this. I've never really had a reason to. I bought it for a project that I never actually did.
But that's a motor controller.
Right. This can drive 2 standard motors or 1 stepper motor.
Good deal.
But there are newer versions that don't have a heat sink so big.
Warning: hot.
wait, what if you?
And there are other shields, mind you,
Falcon shield.
like LCD screens, Wi-Fi, and a variety of other things that we won't get into much. Some Arduinos even have certain functionalities of certain shields built into them. This Arduino right here, the one that has the Intel processor on it, has built-in Bluetooth, a built-in gyroscope, and a built-in accelerometer, which we'll be talking about a little bit later.
Gyroscope tells you where it's at, right?
No,
Gyroscope tells angle,
Angle, yeah.
well, angular momentum. No, angular acceleration, excuse me. Not angular momentum, that's different. And an accelerometer tells you linear acceleration. Okay?
Yeah.
Only 2? Holy smokes.
There's also a temperature sensor in here, but it's a temperature sensor.
Wait, what does that mean? Just like mercury? I don't know how what temperature.
Well, it just tells you the temperature.
How?
Oh boy.
Dude, don't.
I'm just
You-
wondering how
this-
something.
We will go over this later. Not right now.
It has to do with the electrical characteristics of the material that is used to make the sensor and how it conducts electricity when it is at a certain temperature. And then using math, depending on the voltage that you get back, you can actually determine what the temperature is. That's the basic rundown.
Okay.
It's cold in here.
Yeah, it's frigid. Pass cold.
I just use my nerves.
Now,
Cold.
Arduinos
27?
are pretty much programmed exclusively in C and C++. There are other companies that make things similar to an Arduino that can be programmed in other languages. One board, I can't remember what it was. I can't remember who it's made by, but it's called the Yo-Yo board. The Yo-Yo board actually runs Android and can be programmed in Java, and it's about the same size. It's a little bit longer than your average Arduino. There are also other ARM-based boards that can be programmed in Java, JavaScript, .NET and C# I should say. Let me think. What else? LabVIEW is another one. Python. Many different languages. But for most of our purposes, the Arduinos would be what we were sticking with simply because of their ease of use. Now, this section's a little bit wrong. I wrote it in such a way that it's not really right, but for the most part, Arduinos will communicate with the RoboRio through I2C or the digital lines. You could communicate with an Arduino to the RoboRio through SPI, which we'll be talking about what all these terms mean here in a little bit. But the support for SPI on Arduinos is really centered towards the Arduino being the one true controller and not being a slave, whereas the RoboRio is set up so that it can only be the one true controller, which is a problem. You can't have two leaders shouting at the same group of people to do different things at the same time. It doesn't make any sense. So, for the most part, we'll be sticking with I2C for that if we ever have to use an Arduino on a robot, but it's possible that you could use it in other ways. And like I said earlier, Arduinos are used for several different things. One of the ones that I was thinking about using them for this team was a driver station interface. Arduinos can emulate USB devices, which means that they can emulate joysticks, which means that we could write special code that sends information to the Arduino to make LEDs in the driver station light up when certain things happen, give you specialized controls for certain actions, etc., etc. As opposed to having to have another controller or another joystick. Now, one thing that I will say is that Arduinos are somewhat limited to what they can do when they're on the robot. When they're on the robot, they cannot have any sort of wireless communication device. This includes infrared, Bluetooth, Wi-Fi. What is some of the? I think it's RF 900 and RF 450. You can't have any of that on the RoboRio, and you cannot on the robot itself with the Arduino, and you cannot have an Arduino driving motors on your robot. It's not allowed. Any motor driving has to come from the RoboRio itself, in any of the many ways you can do it.
So wait, you can't even have like a little side shooter motor?
They'll have you take it off.
No, that's not fun. I said, well,
This is because of the way that the robot software works. If the field needs to be killed immediately, no, if the field needs to be shut down immediately, like all robots in the field need to be shut down because like a robot is on fire or something. I'm not kidding. It has happened. If a robot is on fire or something, and you've got an Arduino that's doing its own thing, and it's doing its own thing because it still has power, that's a problem. Because they have no way of stopping that. And if it's like an arm or something, or a fast spinning like flywheel, that endangers the field crew. Which is why everything has to go through the RoboRio, because when the RoboRio is told to emergency stop, everything gets shut down. PWM, CAN, I2C, SPI, analog and relay, everything is shut off immediately. And it's not able to be turned back on until the robot is rebooted. It's a hard stop. So that's why you're sort of limited to what you can do with an Arduino on a robot. On your driver station, as long as it's reasonable and you're not causing problems for the computer that the Arduino is running off of, it really doesn't matter. Now the last part of this section is piggyback devices, and Justin was talking about Raspberries earlier, and I guess I should probably take it out. Piggyback devices are in of themselves computers. They're quite a bit more powerful than Arduinos, and they often run Linux or some variation of Linux. On this device here, which it's actually on this SD card, I have something called Raspbian Jessie, which is just a particular version of Debian Linux that is very basic and easy to use. I don't use this for much except as a file relay and a web server, a very basic web server, and I broke it the other day.
Why'd you do that?
It wasn't on purpose. I accidentally installed another web server to try to do something specific to that web server, and I forgot the other one was running, and it broke a bunch of stuff.
Can't use those as like forward.
Wait, you broke a website?
No, well, one of my personal local websites
Oh.
I was working on, not a big deal. I had it stored other places, it just wouldn't work after that. So I just started running it off my laptop. Like if you were on my phone's network right now and navigated to whatever my IP address is, you'd get confronted with a web page. Normally what these devices are used for is for when there's stuff that needs to be done on the robot that is a little bit more intensive than what the RoboRio can handle. Usually they're used for computer vision, where you sort of have a lot more going on than what the RoboRio can handle in a small amount of processing space and memory, and so you need some other device to do the work for you and then just ship the images that you've processed, or the information, even better, because that would reduce bandwidth usage, ship the information over to the RoboRio so that it knows what to do. One other thing that these are sometimes used for is driving LEDs as well. Driving LEDs can be a bit of an intensive process depending on how you do it and what LEDs you use. In fact, the library that I'm writing right now, I will probably write a version of in Python that will run on this, so that should teams have other things going on in their RoboRio that's a little bit more intensive, they don't end up having to deal with the fact that their LEDs are getting in the way of getting the actual processing done that needs to be done to run their robot. Now, one thing that I will say about devices like Raspberry Pis and things like it, which there are all kinds of them, there's Orange Pi, Banana Pi, I'm not kidding, Kangaroos, BeagleBones, there's all kinds of them.
The person who made this was always hungry.
Even the Yo-Yo that I talked about earlier, the Yo-Yo like Arduino device, can also be used as a piggyback device, because it's quite a bit more powerful than your standard Arduino, although it behaves very similarly. One thing about the piggyback devices is that they have to be connected through Ethernet on the robot, or some other communication interface. They can't be connected wirelessly. The only wireless devices you can have on your robot is the radio. Period. End of story. So no IR, no Bluetooth, no accessory Wi-Fi connections except for your radio.
Wait, that's so people can't like go on the phone and like connect to your thing?
No, it has to do with signal interference. The first tries to make signaling in FRC as common and as equilibric as possible amongst all teams. They try to make it so that every team has the same connection capabilities as any other team on the field, which is why every team has their own isolated virtual network for communicating with the Scorpion box, the main server that runs the field.
Oh yeah, I've seen that. Scorpion. Yeah.
There is what is probably a $600 router sitting on top of the Scorpion box that can do all of that and manage all those connections, that has 6 antennas on it. It's one of those things where there's been a lot of thought put into it, and which is why people come around with those Wi-Fi scanners and tell people to shut their hotspots off at competitions when they're in the pits, because them having their hotspots on can affect the field.
Why would you just leave your hotspot on anyways? It just wasted your battery.
Well, most teams use it to look things up and download files and stuff.
If you're at a different school than what your school is, you don't have internet on your computer.
In fact, some competition organizers will actually tell the venue to shut their Wi-Fi off for the competition. Albeit most say no, some will do it because it is a bit of a task to shut down an entire Wi-Fi network. Like the Lewiston Colisee, there's no way in hell. They don't have it set up the right way to actually be able to say, be off for this. No, because it's not one plug. It's a whole series of plugs.
Can't just undo the surge protector. Oh, good.
No. So we're gonna take a minute to breathe. We're already almost at a gigabyte for this session in terms of storage. This one's gonna take a long time to upload. But we're gonna pause, and in the next two sections, we're gonna work through probably one right after the other. That is signal types and basic sensing digital switches. So that'll wrap us around to starting to talk about the meat and potatoes of some of this stuff here.
If you're, you were trying.
Okay.
It was 47.
Enough. So we're back.
I'm just kidding.
They've had some food.
Tacos.
No, pizza.
Dude, no, what would be good? Taco pizza.
Lord. I think they make that. Anyways,
Big Mac pizza.
we're going to be talking about signal types next. Now, there's only two types of signals, digital and analog. And for the most part, what we're going to be dealing with is digital signals. But I do have to talk about both because some sensors do only work, well, some sensors do have the capability of working with analog, and there are a lot of them that do work with analog. But for the most part, we're going to be using digital. But that being said, let's talk a little bit about this, which I probably should have gone to the bathroom before I came back over here, but that's okay.
Just pause it.
No, I'm okay right now, but
It's not good for you.
mostly because I'm just cold. It's freaking freezing over here.
I know, it's cold over here, too. That would be a little girl. Right, it's really cool.
So in terms of different, pay attention. In terms of different states, this is the easiest type of signal to deal with digital, because it can only be on or off. A 0 or a 1. 0 being off, 1 being on, obviously. All of the communication protocols that we use in the RoboRio are digitally based. Whether it be SPI, I2C, UART serial, PWM, or CAN, they're all based on digital communication. There is no analog signaling there. Changes in digital signals can happen extremely rapidly in micro and nanosecond time. Now, do you guys know how small micro and nanosecond time is?
Is it like
You can't see it.
So
It's time. You can't see
you can't see time, genius.
and you can only see,
microscope.
you can see 25 frames a second, so.
So
That's
Dude, what does frames?
listen to me.
how many pictures, how many
A microsecond is 1 times 10 to the negative 6th power seconds.
So 1 million.
Yes, actually.
Yeah, that's
See,
like
if I-
And a
said that, you
nanosecond
said, like,
is
the-
1 times 10 to the negative 9th
so 1 billion.
seconds. Or 1 billion. I think of things in exponential notation.
Yep.
It's just easier for me.
Scientific notation.
So, if you're having an issue with a digital signal, it can be hard to diagnose what might be going wrong on the signal level, should you be having an issue. That's why things like oscilloscopes exist, which can actually show you in real time, over a period of time, what a signal has done. And then once you've gotten that information, then you can zoom in and be like, okay, at time t equals 100 nanoseconds, the value is this. But in most cases, I should premise this with, Justin, stop playing with the can or I'm going to take it away. I don't care if you're trying to drink from it.
Do you have ADD?
No.
I'm beginning to think.
Taco signal.
Anyways, in most cases, if you're having an issue with a digital signal, it's not the digital signal itself, it's the code that you wrote to make it happen. Digital signals are very hard to screw up on the hardware level because everything about a computer is a digital signal. It's a 1 or a 0. It's just basically how it works.
So if you're going through and you have a 2, that's your problem.
Oh, okay. Anyways, digital signals can be converted to analog signals using something called a digital to analog converter, which basically just takes in a series of 1s and 0s, makes it a decimal number representation, and then based on a certain range of values, usually either 0 to 1024 or 0 to 4096, it takes the ratio of that value and then puts out that percentage of voltage
That you
on a
apply.
wire.
So if you like only move it halfway,
So if you were
50%.
if you were doing like 1024 and 4096, 1024 is 25% of 4096, right? So then if you had a 5-volt signal, then you would push out 25% of whatever 5 volts is,
So 1.2.
1.25.
Oh yeah, okay, man.
So that's basically what it boils down to, right?
No, it's 1.2.
No, what is it?
1.2.
1.2? Are you right?
Yeah.
25% of 5
25%.
is 1.2 is
Okay, so half is 2.
my brain is hurting. Somebody help.
Half
Somebody. Yeah,
half of
I think
5
you're right.
is 2.5.
No, because 1.25 plus 1.25 is 2.5.
Oh, you're right.
I'm having such a rough day. I didn't sleep good last night.
Me either.
Uh,
I never sleep good.
but anyways,
Sleepy's on me.
the reason why you would want to have a digital to analog converter is if you wanted to put like speakers in the robot or something.
You can't do that though.
No, you can.
You can?
Yeah.
So we can be on the
Yeah.
thing, and when we hit into someone, it go.
Yeah. I mean, if you wanted to waste the power.
Or when we're going full
Or
speed,
when
it
we
go.
break something, it says, Justin, stop doing that.
Or when we're going really fast, it does the warp sound from Star Trek. No.
No, from
When we fire your shot,
you could. Just another thing that you gotta waste power on.
Like when your robot's about to blow up, you have an air raid.
But that's not really something that we have a problem with dealing with.
Self-destruct initiated.
Simply because there's plenty of resources on the internet if you want to learn how to do stuff like that. And push come to shove, this is not really something that we're going to have to deal with.
Please remain calm.
Now, analog signals are very different. Analog signals are a range of voltage. It's not on and off anymore. It's 0 to whatever your reference voltage is.
100.
No.
1.
oh, that
To
makes
what
sense.
your reference voltage is.
Oh,
If you
so
would
12.
listen, no, not necessarily.
Okay. 12.95.
No, it's
Still not necessarily.
That makes me
Okay, listen to me. Your reference voltage can be literally anything. In fact, on an Arduino, it can be anything from 0 to 5.
So why are you telling me no?
Because you kept rattling off just different numbers. It can be literally anything.
Okay, so any number.
Yeah.
The possibilities are basically endless. As long as the pins that connect to the device that's reading that voltage can handle that voltage.
Don't
mind
be
you.
sticking 120.
So, wait, why would you have too much voltage?
It blows
You burn
up.
out the pin,
So
and then you...
don't be
could
plugging
damage
a
the
Robo
processor.
Rio into an outlet. Probably wouldn't end good.
Well, it's because they're two different types of current.
Yeah, DC and
Wait, we run on AC? I mean DC?
Yeah, all batteries are.
Huh?
All batteries are DC.
Yeah, I know.
There are some batteries that are not directly AC out of the terminals. In terms of storage type, yes, batteries are DC. But there are some batteries that you can purchase, like electric vehicle batteries that natively put out AC.
Yeah, I got some books from the library about like how AC, DC, and all that. Because of the program, they'll learn more about mechanical and all that stuff, electronics. So I got some books in there that read 400 pages. Just enough to scan.
Oh, come on, that's not that bad.
I'm a slow reader.
And
I scroll syndrome.
my junior year of high school, I read 3 books on quantum physics.
Dude, that's not
Just for fun.
I just know that during Big Bang, that quantum levels is like huge.
Dude,
at base, when space expanded in Big Bang, quantum is now huge. So
Quantum computing, it's the way of the future.
Okay, so we're going down a road, and we are like, pew, pew, pew,
He can
pew.
edit it
Oh,
out.
where'd the road go?
You can just edit it out.
Doesn't matter.
Yeah, make sure to. Like,
Anyways, we did get off topic.
You have to do a click.
So reference voltages are normally specified in hardware, like they're hardwired to a particular voltage, but Arduinos are a little bit different. They actually have a pin on them called AREF, which means analog reference.
Wait, can you pause the video?
Yep. So we're going to keep going. We had a short discussion about some stuff. And they won't stop making stupid faces.
You know. Oh, it's going up.
My phone is getting warm in my pocket. I don't know why.
Your body's producing lots of heat and
No, I'm not producing that much heat. Oh.
What?
What the hell?
Your phone blowing up?
Well, I don't really know what's going on. Something's not right. I think the hotspot might have messed up my network connection somehow. So I'm gonna shut it off for now because I don't really need it. I'll have to. I'm not really sure what that H means. HSPA plus. Well, anyways, doesn't really matter. So let's continue.
Why are you doing squats?
stay warm.
So analog signals are used for things like audio and potentiometers and other sensors. And we'll talk about potentiometers in a little bit here. And we talked about a little bit about how you relate an analog voltage to
Digital.
a digital signal. But in terms of sensors, you could say that if you had a potentiometer, which is just a variable resistor, something that resists a certain amount of energy, you could say that if you turn a resistor, a variable resistor or a potentiometer 1 millimeter, then that could equal 1 millivolt. And then you could determine the angle of the potentiometer based on how many millivolts you read from the sensor itself. Does that make sense?
Yeah.
Okay.
That's how I figured it would work.
So analog signals normally have something called a resolution, and while the video was paused, we did talk about this a little bit. Resolution basically just means how many bits of data are being used to represent the analog voltage as a digital signal. Because computers can't natively read analog signals. It needs to be converted to digital before they can understand it.
Oh, yeah.
So you have a particular resolution to determine whether or not a value is something that you would expect it to be. Now, that grating noise. For the most part, what you'll see is either a 10-bit resolution, which means that there are 1,024 possible values that could be used to represent an analog signal as a digital one, or a 12-bit one, which means that there are 4,096 different values possible for representing a voltage. Now, of course, 10 and 12-bit are not the only ones. I did just see, I subscribed to emails from the electronic parts servicer DigiKey. They just had a company release a analog to digital converter that has a resolution of 24 bits, which is a massive number. It's something like something like 167 million.
Does that like take pictures of a lightning bolt that had behind a stand? Right?
Taking pictures is a little bit different. It's a little bit.
Oh my goodness, get back on the road!
It's
He just cut it out.
it's a little bit different. And it's something that we could talk about another time. But Justin is right. Let's keep going. Because Justin is apparently cold. You tried being cold 24/7, 365.
You were the one that took your jacket off.
Yeah, because I was actually getting hot at that point.
Yes. What's wrong with you?
The RoboRio, in of itself, actually has 12-bit resolution on all of its analog channels.
Pretty good.
So it's not really all that bad. If you were trying to figure out how many bits of resolution your particular analog connect, or how many different, so like if you wanted to know 1024 or 4096, numbers like that, how many different possible representations there are of your analog signal, then all it is 2 to the power of the number of bits that you have available to you to use. So 2 to the power of 10 is 1024. 2 to the power of 12 is 4096.
Good deal.
2 to the power of 24 is some ungodly number. One thing that I will say about analog sensors in particular, they are very susceptible to noise. That is electromagnetic radiation that can affect the signal as it travels across a wire. Digital signals are also affected by this issue, but not nearly as much, because all you have are 2 states, either on or off. So as long as the value is above some threshold voltage, that can be considered as on. And if it's below that threshold voltage, that can be considered as off. However, with an analog voltage, you're trying to be much more accurate. You don't want that voltage to change if you want to read it as something specific. So if you get a lot of noise, like from a motor or a very large magnet, then you have a problem.
So what about like radio with that?
The radio,
Or battery?
the battery more likely, I would think. That's hard for me to say. The radio probably would not be. The radio would probably not be able to create an issue.
What frequency does the motors make, or is it like a white noise type thing?
It's sort of like a white noise type of thing. It's not really frequency as more of the magnetic field that they create when
Yeah, that's
they're
right.
running.
That's if you run them.
So you really got to be and the way I described, if you were looking at the output of an analog sensor that was being subjected to noise, the way I put it in my notes is the signal would look like a voltage value that's sort of trying to hover around. Well, the exact wording is, while looking at the output of an analog sensor on a number display, you can usually see a small amount of noise in the signal by looking at a voltage value that comes out of the decimal point, which usually jitters about like a madman on cocaine. And it's basically what it looks like, is there's always a little bit of noise, and it's always a little bit of jitter around one little point.
Well, that shouldn't be too effective.
If you do averaging, which is what a lot of people do when they have an analog sensor, or they use noise filtering, then that can usually help and alleviate most of the issue. Like when I do the battery carts displays and sense the battery voltages, I'm going to take 10 or 20 samples over the course of like a second and then average them all together.
Wait,
and use that as my result.
Could you insulate the like magnetic field? Or no, you can't. I was thinking if you insulate the magnetic field of the motors.
You would have to build a Faraday cage around the motors, which would not be easy, and it'd be clunky. It blocks out noise, electromagnetic waves. But anyways,
pretty much just wrap your.
Next thing that we're going to be talking about, digital switches. Now, obviously, you guys know what a switch is. On, off.
Wait, you mean like a 0-1 switch?
Yeah, I mean like just on and off. Like a standard light switch is a 0-1 switch. You know, there's not really that much difference there. Oh, gotta get comfortable here. Sort of. Now, there's nothing much simpler than switches and buttons, so we won't spend too much time on this. But switches are good for selecting the modes of something, creating quick input. Now, if you actually combine switches together, you can actually create more options. Now, what I mean by that is, let's say that you had two switches. Both of them can be either on or off, right? Well, what if you wanted to represent 4 different states with 2 switches? Could you do it?
Sure. Quantum. I don't think
The answer is yes. And the reason being is because both switches can be off, one or the other can be on, and both can be on.
Oh, and that's why the more switches you have, it goes up the amount of...
Right.
That makes sense now.
It's actually the same thing that I told you before about analog resolution. It's 2 to the power of the number of switches that you have. So if you had 3 switches, then there would be 8 possible combinations that you could have.
4, 16, 5, 32, so on.
Right. Binary progression.
Wait, so if you have 5...
Wait, so with if you would, quantum, how many switches?
Let's continue. So the next... digital switches are basically done. You can pass an analog signal through a digital switch, but all that's going to do is make the analog signal behave like a digital switch. It's not going to make it behave any differently. Unless, of course, the analog is less than the threshold voltage, then that would be a problem, but that's still different. So the next thing in basic sensing is potentiometers. Potentiometers are those variable resistors that I was talking about before. They resist a certain amount of energy flowing across a circuit. Normally they're used to find the angle of something, usually an arm or a wrist of some kind, and they're not used for all that much else. They can be used for things like volume knobs and things that are outside the scope of what we do, but still useful.
So a turn dial.
When selecting a potentiometer for a task, it's best to think about the range of rotation that you need first, because not all potentiometers have the same range. Some potentiometers can only turn 180 degrees. Some potentiometers can turn 360 degrees. Some can turn 270. Some can turn 720. Some can turn 1080. There are a lot of different combinations with a lot of different resolutions that do different things. Now, for things like robot arms and wrists, a 270 degree potentiometer should be plenty, because there's no reason why your arm or your wrist should be doing a full 360 at any given time. Like, have you our wrists only do about 180, at least in the up and down action area. Now, granted,
I think we need to have like a propeller on the front.
I think that.
a propeller.
I don't know.
I like.
If we need to like
Something that is going through constant rotation is a different type of sensor called an encoder, and we're gonna get there.
I like that the main thing would just
try and break it.
No, wait, I stopped.
Like
Now-
we need a real something.
If you're still having trouble, if for some reason you're breaking potentiometers because you're overextending them, which will happen if you overextend them beyond their acceptable range, you need to be paying attention. They're genius. Then just go for the next size up, or go for the next couple of size up. It's really not going to hurt anything. You'll still be able to tell, based on the number of millivolts you're getting out of the potentiometer, where its position is. You'll lose a little bit of resolution at that point, because you're obviously going to a wider range with the same number of bits to represent that range, but you'll still be able to get a relatively accurate measurement. The other thing that you want to consider is the resolution of the potentiometer itself. The resolution of a potentiometer is measured in ohms, or a particular amount of resistance, as Tyler mentioned earlier.
Okay, time out.
Okay.
I'm being Tyler right now. What does UF mean? Like on a little.
Microfarad.
What does UF mean?
We do not discuss capacitors in depth in this session, but I can tell you later.
Okay.
Do you pay to teach us this?
No.
No.
You just do this for fun? What are you doing here?
Freezing to death. That's what I'm doing.
Dude.
Anyways,
Wait, you do this for your free will and you just enjoying it. You have no life.
Shut up, guys. You have a life.
I'll make something clear after the video here, just so you know.
Oh boy.
But we're off topic, and no, it's not bad. It's just not. It needs to be made clear. So, like I said, the next thing you want to consider is the resolution in ohms of the potentiometer. Now, for most applications, a 10k ohm potentiometer is plenty. 1k, more often than not, is plenty. Simply because all you're trying to do is figure out an angle. You're not doing anything that's super sensitive, and even if you ramp the resolution up all the way to like 1 megohm, you don't have the resolution to read, using the RoboRio, that many different possibilities. If you were using the 24-bit digital or analog to digital converter that I was talking about earlier, then you'd have plenty. 1 megohm might be too small. You might want to jump to 10 megohm potentiometer. But
That's a little big.
Usually, for most cases, a 10k ohm linear potentiometer is accurate enough for most tasks. Now, the reason why I say linear is because there are also logarithmic potentiometers. You guys know what a logarithm looks like, right?
No, I don't.
It starts off rising very fast, and then all of a sudden it starts to level off.
Oh, linear max, yeah.
Yeah.
Alright.
So that's a logarithm, and there are potentiometers made to behave like that. for our applications, logarithmic potentiometers are not useful. Simply because normally we're trying to find the position of something based on an angle. And if you've got a whole bunch of resolution starting at the very beginning and then almost no resolution at the end, that doesn't help you. Okay? Now, I believe, with the comment on logarithmics, yep, we're on to the next bit. So, we're out of basic signaling, and now we're in regular signaling. Specifically, we're going to talk about one of the signals that we use the most, which is PWM, or pulse width modulation.
You talk about this a lot.
Now, PWM starts in with our communication types, specifically the digital communication types, because obviously all of our communication types are digital. PWM is normally used for controlling motors, however, it can be used to read signals from sensors, albeit reading signals from sensors using PWM can be exceptionally difficult.
For you or for us?
What about organized?
For me and for you. I personally don't like using PWM for reading. Okay, I'll premise this a little bit differently. I don't like using PWM in its conventional sense, which is reading the time between pulses. Because whenever you have a PWM signal, all it is a signal that's being pulsed up and down for certain amounts of time. And by changing the length of the pulses, you change the signal that's coming through, right? Sort of, actually. You're actually not wrong. Some PWM sensors produce a synthetic analog voltage because remember how we talked about the water valve idea?
Yeah.
By turning that signal on and off really fast, you can sort of create a synthetic analog voltage which will work for reading the sensor as an analog sensor, but it's not terribly accurate. It creates a lot of noise simply because of the way electricity works and the electrical characteristics of the wires that you're using, etc., etc. So it's not as good as some other things. Yes?
Wait, can you pause it?
Yep.
It's going to be really quick.
Back to the show.
Sorry,
Now, like I said before, PWM works by pulsing a digital signal on and off for particular amounts of time to create a signal that can either be interpreted as a digital signal or an analog signal. This is because the speed at which PWM signals normally change in microseconds of time. Now, obviously, to do all this turning on and off takes a lot of processing time. So the thing that actually manages the PWM timings on the RoboRio is not the RoboRio's processor. It's actually the FPGA. The FPGA actually has special timers dedicated to each PWM channel that can just be told, hey, go at this speed. And they'll be like, okay. And it will do that on that channel. And it takes a lot of the grunt work off of the RoboRio to try to do the timing of, when something should be on, when something should be off. Imagine having to do that for every single PWM channel for every single motor that you're running. Some teams use all 10 PWM ports on the basic PWM ports on the RoboRio, and there's even more on the MXP port. So, it's one of those things where it would take a lot of processing time for the processor to work on, whereas in the FPGA, there's an independent circuit for each PWM channel, and all the processor has to do is say, hey, can you go at this speed? And the FPGA will be like, okay. So.
If I'm never gonna say okay, I'm gonna be like with you.
Okay.
So you gotta look both ways.
Okay.
So, and as I mentioned earlier, due to timing and accuracy issues, PWM is not usually used for sensing. It's usually used for motor control. Just that rapid switching is not particularly accurate.
causes magic like smoke.
No, but it can create a lot of
Bad
noise and variance in the signal that makes things
Bad reads.
that can make things a little ugly. So we're actually all done with PWM. You guys have any questions? I mean, you guys have been
I've
asking.
been asking.
You guys have been asking questions, which is good. So,
Yeah.
and obvious, I guess I forgot to premise this video with this. If you have questions, you can obviously reach out to me in whatever way you can, and I'll answer them the best that I can. If I don't know something that you ask, I usually look it up.
Like and subscribe.
But for the most part, this video is centered more towards Justin and Tyler at the moment. But really, once I have more time, the objective is to make these tutorials actually a lot more useful for the team. That way, should something ever happen to me, at least there's something that you guys can use to continue to learn and teach the next generation.
Next generation. Yeah, because when you have a job and you can't come here all the time. Oh wait, what was the reason? I mean, I sounded kind of rude when I said you had no life. I just.
We'll get there. We're still on video.
God,
we are.
And we
I
still-
thought we were.
And we still got more stuff to talk about.
Alright, I apologize.
We're getting there. We're doing good. We're doing good. We'll probably stop around 4, simply because this video is starting to get exceptionally large.
But can we take a
It's
break?
1.8 gigs, and it will be 2.25 by the time we're done.
Dude, why not you just?
You have to be.
Dude, and my toes I can't feel.
Well, that's what people.
We're gonna take a short break,
We should migrate.
and we'll continue here in a minute.
Hey, boy.
So we took a little bit of a hiatus. Okay. So Justin's sitting over there now, and Tyler's right up on top of me now. We're going to talk about at least CAN and I2C before we're done here today. They're not exceptionally long sections, but depending on how long they take, we may do a little bit more. It is getting cold in here, and I'm getting tired of shaking. So, CAN stands for Controller Area Network. And, well, it's not necessarily used for sensing in robotics. CAN is still something that we want to talk about because it's part of how the RoboRio communicates with some of its other devices. In particular, the PDP and the PCM, the power distribution panel and the pneumatics control module, are both CAN devices. They communicate through CAN. And while there are multiple different ways that they could have hooked up the PDP and the PCM to the RoboRio, but CAN was the simplest simply because of the fact that it only uses 2 wires, and it's very easy to, let's say it this way, it's very difficult to screw up CAN. As long as you plug the wires in right, it will basically work. Now, the reason why the pneumatics control module has CAN should be obvious. Obviously, if there's no connection to the pneumatics control module, you have no way of instructing it to do something. So we have a CAN connection to the pneumatic control module so that we can actually tell it to do things. Now, we don't get into pneumatics in this session because this team probably won't use pneumatics very much because Mr. Klein does not like them. And there are reasons why I like them and don't like them and whatever. But it may not be as obvious why the PDP, the power distribution panel, has CAN. The PDP has CAN because there's actually a small computer inside the PDP that reports back energy usage information to the RoboRio so that it can be logged and kept track of and viewed later on the driver's station should an issue arise. Like if you wanted to see where a whole bunch of your power was going when you were driving around. Normally, CAN is used in cars, trucks, and other vehicles to provide diagnostic information. Specifically, you know how some cars, well, all cars after 1998 have a little connector. It's usually purple, and it's either under your steering column or inside your glove box or something like that. It's got a whole bunch of pins on it. That is called the onboard diagnostics port, or OBD2.
Oh, and you like plug
port.
stuff in and it can like mod your truck.
Well, not mod your truck, but you plug stuff in and it can give you diagnostic information about your truck.
Can't you like get one that like turns the fuel like way up? And
That has to do with changing the control module. It's something completely different.
Wait, you can make the car faster by just like putting stuff in.
Some vehicles, yeah. We won't get into that. The reason why they use CAN like this is because it's designed to be a hostless communication protocol. Any information traveling across the CAN bus can be listened to by anybody.
so it's global.
It's like what Hillary did with her emails.
Right.
Shut up, Tyler.
But
Fog it up.
because it's hostless, you know, the devices that are on the CAN network, like sensors and stuff, specifically in cars, sensors and stuff, can just sort of start broadcasting information, and the car's computer can pick up on that information and make it something useful to the vehicle and the rest of the systems in that vehicle. Now, CAN can actually also be used for controlling certain motor controllers, specifically the Talon SRX,
Dude,
which
I
is the
should've grabbed one.
which is the newest Talon, and the IFI Jaguar. Granted, the Jaguar really isn't used very much anymore. Stop it. The next communication type that we're going to talk about is inter-integrated circuit, or I2C. And I talked about I2C a little bit earlier when I talked about Arduinos. I2C is actually one of the ones that we'll be using much more commonly when we talk about sensors. I2C consists of two digital connections, a clock line, which just turns on and off at a particular speed, and a data line. You can only have on a standard I2C connection, I should say. There are different versions, but on a standard connection like what we'll be using. Really? Pay attention.
I'm listening.
On a standard I2C connection, you can have 128 devices.
That's a lot.
Which is a lot, and it's a lot more than we would ever use. Like on our battery cart, there will be 13 I2C devices all on the same I2C bus. The Arduino itself and the 12 screens that will display our voltage information. Those all communicate through I2C. Now, as I said before, the SCL, or the clock line, keeps accurate time between devices connected on the network.
Can I have a copy of one of those?
A copy of one of what?
Those.
This here?
Yeah.
Yeah, I mean, I'll probably put it in the group chat when I'm
Alright.
all said and done.
I want one too. So.
Whereas the SDA, or the data line, is used to transmit the actual data bit by bit until it reaches its destination. Now you may be wondering how I2C determines who listens to what information. What exactly are you doing? He's using my laptop fans to heat up his hands. Let me see. Where was I? Just now I forget where I was. Oh, that's right. Every device on an I2C bus has an address, which is where the whole 128 thing comes from. These values are normally between 0 and 127, and for our purposes, that's the range that they will be within. And like I said, however, there are some I2C buses that allow you to connect more devices than just the standard 128.
Okay.
Yeah, I turned the fans up.
How'd you do that? Oh. Well, now it's cold.
I'm not doing anything. All I got is programs open. It's just sitting there. Anyways, one thing that I would like to mention is I2C is a connection type known as open drain. And basically what that means is rather than the signal lines, the clock and the data lines, starting at 0 volts, they start at their reference voltage, which for the Arduino and for the RoboRio would technically be 5 volts. And basically what you do is, to pulse the line, you connect the line to ground, turning it off rather than turning it on to represent a value.
What? So off is 1?
No. So imagine it like this. Imagine if it were normal convention to always leave lights on. Okay? As opposed to leaving lights off.
Oh, okay.
That's I2C. Rather than the convention leaving the lights off, you're leaving them on, and for whatever reason later you're switching them off to mean something.
NRX.
Pay attention. What is wrong with you?
I think it's...
Anyways, this is done by using something called pull-up resistors. Basically what you do is, on the data and the clock line for I2C, you connect a resistor to each line and then connect that resistor to whatever your reference voltage is. In our case, it's 5 volts. Now, the RoboRio does have built-in pull-up resistors, and at least if I remember correctly, they do. It does. I'd have to double check. It doesn't actually say in my notes. But with I2C, if you have multiple devices with pull-up resistors on them, the bus won't work. You can only have one set of pull-up resistors on the line, otherwise the bus won't work correctly. So you need to make sure that if you have any sensors or something that have built-in pull-ups, you disable them or you take them off, which most sensors will give you the ability to like cut a pad or a trace or something to disable them, rather than having to unsolder them. So we're actually moving on quite a bit quicker than what I thought we would, so I am going to keep going. We'll probably stop in another 15 minutes or so here. This has only been an hour and a half long, which means we've been pausing a lot more than what I expected to, but that's okay. So the next thing that we're going to talk about is SPI, or the Serial Peripheral Interface. SPI is a 4-wire interface. Most of the time. SPI has to have at least 4 wires to function correctly as an SPI bus, but it needs another wire, another connection for each device that you add to the bus. So it does start to go up in the number of pins that you have to use to communicate with multiple devices as you keep going.
What is that? Would that be like a higher load?
There's a particular reason why you would use SPI over I2C, and for the most part it's speed. SPI is much faster, whereas I2C is slower by quite a large factor, but it's a lot more robust in terms of being able to quickly add and remove devices. Does that make sense?
Yep. Sorry.
So, no, you're fine. That was an appropriate question to leave on the video. That's fine. The first wire is the clock line. Same as with I2C, there is a clock line. It's controlled by the master device. On this type of bus, there is always a master device. And I should have mentioned that with I2C. I2C also always has a master device.
So is that the RoboRio?
Yes. So, in terms of all of this discussion, if a bus like I2C or SPI has to have a master, the master will always be the RoboRio. Simply because the RoboRio doesn't function well as a slave, which they are called slaves. It's just the way that the terminology works.
Was it created in the South?
No. Anyways, the clock line is controlled by the master to keep every device on the bus timed correctly. The second wire is normally the master out, slave in. This is the data coming from the master to the slave. Okay?
Okay.
I know it's really
Terminology.
bad terminology, but you
Is it
gotta look at it.
reptile?
I
It
mean,
doesn't work.
you've gotta look.
With it.
You've gotta look at it from the different perspective, okay? So like if I were talking to Tyler now, Tyler, you are not my slave, but this would be the master out, slave in sort of communication style, where I'm saying stuff to you and you are taking that information in and doing something with it.
All right, so
In this
You
case,
like
you're
say-
supposed to be remembering it.
what the- no.
I know, which is why I really don't like having to do this really rapidly. This is the sort of thing that I should be doing over like a year's time, and we're only going to be doing it in like 3-4 months.
Brad,
So
we are not slow people.
Yeah, I'm in accelerated classes.
Yeah, we are need for speed. Like.
But anyways. the data,
Red line.
the third wire is master in, slave out. So that would be like if Tyler was telling me something. And then the final line or set of lines is called, and this is much, much worse, SS or slave select. It can also be called chip select. But in fact, chip select is becoming a lot more common than slave select.
Wait, what's chip select mean?
Chip select just means you are trying to specify which device on the SPI bus you're talking to. So like, a chip select would be like, I point at you to tell you that I'm talking to you. Or you point at, or I point at you and then you start talking to me. Same thing with Justin.
So
If I point at Justin,
so it
then I
runs-
want to talk to
so
Justin.
so I remember what I'm doing. You point to me, then I do it. And that
Right, so
runs-
I point to you and start telling you what to do,
Look
Yeah.
at
and
it
you
as a
start
band.
doing it.
Hey, Tyler, look at it as an orchestra director.
Yeah.
You do this. You do that.
Right. I point to you, tell you to do something, you do it. I point to Justin, you're not listening anymore. Justin does what I tell him to do, etc., etc. Back and forth like that.
the mail's gonna take your heat.
Now, one thing that's really cool about SPI, and one of the things that makes it faster than I2C, is SPI is a synchronous protocol. Meaning that, and this wouldn't work in real life, but I could talk to you while you're talking to me. So I could point at you and start talking, and you could point at, and you could start talking at me, and I would be able to understand what you're saying and act on what you're telling me to do as you're acting on what I'm telling you to do.
Listen, you
I
go.
want
Make
to try
a, you go make a peanut butter sandwich.
So,
that.
SPI's most common use is with SD cards and smaller LCD displays. However, it is extremely useful for connecting the RoboRio to other devices. Arduinos, I put in here that it's nice to connect it to Arduinos. That's changed a little bit. Some Arduinos do have some healthy SPI slave support because the RoboRio has to be the master. But because of the way that the Arduino libraries are written, it can be kind of hard to make some Arduinos behave as an SPI slave, but it is possible. It just requires a better programmer. Could I do it? Yes. Do I want to? No, because I have to use the actual registers, like the low-level assembly style stuff. Not really assembly, but the registers that represent the bit level actions of what I'm doing, and it just pain in the butt. So I really don't want to. Now here's the thing. Because of the way SPI works, slaves cannot communicate with other slaves unless the data goes through the master first, and then the data goes out to the slave that it was intended for. There is no inter-slave communication on SPI. So for Tyler to say something, I know, it's bad, but just bear with me here. So if Tyler wants to talk to Justin, Tyler can't point at Justin and say, hey, I need you to do this thing for me. Tyler has to wait until I point at him. He tells me what he wants Justin to do. I stop pointing at Tyler. The next time I talk to Justin, I point to him and I say, Tyler wants you to do this.
So that could take a while.
So would that be like turn on a light, like LED light? Is that what would it be used for?
What, SPI?
Yeah.
You can actually, with some types of LEDs, you can use SPI to communicate with them. In fact, the LEDs that I'm working with and I'm trying to get working on a RoboRio actually use part of the SPI interface to communicate. Albeit they can... Oh my god. Albeit there are other ways to communicate with them. SPI is the fastest because of how fast SPI is. The clock speed on the RoboRio for its SPI bus is 4 megahertz. So 4 million on-off clock cycles in a second, which is a lot when you think about it.
Yeah.
Especially for LEDs. I mean, you could do a lot of... Have you ever seen a persistence of vision example where someone put something on a rotating disc?
25 rotations per second equals how much you can see. Yeah.
So, we're still a little bit ahead of the game. I'm going to do one more section, I think, at the very least. I know, you're cold, but we got to get through this stuff, Justin. Like I said, I might not be here next weekend, and if I'm here next weekend, I'm not here the weekend after that. So, we've got to get through this.
Well, if you send that to us, I could do some research for a few hours.
I know, and I will. I'll put it in the group chat, but,
Print it out.
anyways, the next step is another signaling step. RS-232 and Universal Asynchronous Receiver Transmitter, or UART. Both of these communication types are serial communications. That means that you send data, you receive data, you send data, you receive data one at a time, blah, 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 blah. And it's peer-to-peer communication, which means it's one device communicating with another. It's not bust. You can't have multiple devices on a serial connection like this. It just doesn't work. And both RS-232 and UART work on the same general principle, but they are not the same. If you tried to connect the two together, they wouldn't work. In fact, you could probably damage one or the other in the process. So you got to be careful of that. There are actually two different ports on the RoboRio. One is an RS-232 port, and one is a UART port. The RS-232 port is broken out as a standard header. You can actually see it on the RoboRio if you look at it. It says RS-232 right next to it. The UART port is actually on the MXP, that big rectangle in the middle of the RoboRio.
They have to buy
Oh, yeah.
offboard for.
Well, you don't have to. You could just put pinning wires on there and it would work. Like, I could make a PWM cable and make it work. It doesn't matter.
Looks weird.
Yeah, it would look weird, but... Anyways. RS-232 and things like it were actually used for quite a long time until USB devices came along. Modems, UPC code scanners, joysticks, all kinds of stuff made use of that protocol. Now that USB can emulate RS-232 and UART communication, it's just really not used anymore. It's just not... It requires too much, because it requires too much to actually make it work in terms of a regular hardware interface rather than just doing it over USB. Now, the communication speeds for UART and RS-232 are fixed, meaning that you can have variable speeds, but you have to like hard program them into your code. You can't change them on the fly.
Set in there already.
Right. They're set in the code, and that's the way they need to stay. They're measured in baud, which really doesn't directly relate to any other... Like, it doesn't relate to a bit rate, really. I mean, it sort of does, but there's variability in the communication style that can cause it to not be exactly what you would expect it to be for a speed. But higher numbers are faster, and that's all you need to know. And they are fixed numbers, like 9600, 38400, 115,200 is another common one, and there's all kinds of them. All the way down to 200, I think, which is exceptionally slow. Alright, I think what I'm going to do is I'm going to round this video off at 2 hours. Now, we've only got another 15 minutes left to get to 2 hours. We're getting there. I promise.
Money Cup 2 spans lost.
I have got to try to get as much of this done as I can.
Alright.
So that way we have as little to do the next time we meet as possible, so I can start talking about programming sooner rather than later.
Alright, let's do this.
So, the next thing is going into sensor specifics. And what we're starting with is ultrasonic sensors. Now, ultrasonic sensors use super high-pitched sounds that are well out of the range of human hearing to measure distance. Now, you both know that the speed of sound is a fixed speed, correct?
It depends on the thickness of the atmosphere.
For our purposes, Tyler.
So 720 miles per hour.
Yes, Tyler.
Okay.
If for some reason we were doing this at
Mountain level?
mountain level or up in space, we would have a problem.
Well, there's no sound in space. We'd be doing it like.
I'm,
Sorry.
I'm talking like the edge of space, Tyler, not space, but the okay.
The
Anyways.
troposphere, there's very little.
Anyways, as long as you can determine the amount of time between when you send out the pulse and when it bounces off something and comes back,
Amount of time you can divide over distance, and that's.
right,
Yeah.
you can figure out the actual distance that you traveled or the sound traveled.
I can do that.
Now, the range of ultrasonic sensors varies wildly from sensor to sensor. You'll need to figure out what distances you need for your purposes and check the manufacturer's information before making any purchases. Otherwise, you could end up with something not accurate enough to do what you need to do. A lot of ultrasonic sensors vary from, as close as 3 centimeters to the sensor to as close as 30 centimeters from the sensor, and a range of a foot to a couple of yards or more. I saw one ultrasonic sensor the other day that you could be sitting at the halfway point of the field, and as long as you had a straight shot to the wall, you could still measure your distance from the center of the field to the wall.
That's a strong.
Now, for the most part, you'll find that ultrasonic sensors will communicate through either just basic digital communication, where you send out a digital pulse that causes it to trip a microphone to play a sound, and then when another microphone hears a sound, it will activate a digital output, and that's how you...
So what happens if there's two robots, and one's facing the other, and then one shoots it, and then the other shoots it, and...
we'll get there. We're going to get to the problems of ultrasonic sensors in a minute.
Yeah, do they use different frequencies, noise to?
We'll get there in a minute. But we're almost there, I promise. There are other ways to communicate with ultrasonic sensors as well. Some simpler ones communicate through analog signaling, as well as RS-232 UART serial. You can also find ultrasonic sensors that communicate with other types as well, but they're not as common, and for the most part, they're not as useful. And now we're on to the issues, which these two mentioned just a second ago. There are several issues that can present themselves when you're working with ultrasonic sensors. One of them being, if you've got multiple ultrasonic sensors that use the same frequency of sound to communicate and measure distances, then you have a problem. Because while the microphones and speakers used on ultrasonic sensors are very conic, they're very focused to point in a certain direction, you can still have crosstalk that can create issues in the long run. While this doesn't happen exceptionally often, it's still a possibility that you should be concerned with. But for the most part, as long as you're actively sampling your ultrasonic sensor, it's really not that big of a deal. Now, there are other issues. Obviously, if something is in the way of you and the target that you're trying to measure your distance from, like another robot, then you have a problem. Because obviously, sound bouncing off the robot is not going to be the same distance as sound bouncing off the wall that you're trying to measure the distance to. So that can also cause other problems. And the other the other major issue with ultrasonic sensors is the surface that you're pointing. So you guys both know that sound propagates as a wave,
Mm-hmm.
and you know that an angle of an object can change how a wave travels. Well,
So wait, if you hit a corner
if you pointed an
Or a
ultrasonic
slant.
sensor at a corner,
or a slant, it's gonna go.
it may not all go.
What's if
brrrr.
if it's a foam surface, will it not be able to see it? Like,
It depends on the intensity of the sound that comes out of the ultrasonic sensor, how focused it is, and the absorptive properties of the foam. That's a bit more complicated.
I just wondering.
But obviously, if you hit an angle, not all of the sound that you send out is going to come back, which means you may get inaccurate readings or no readings at all. So it's another thing that you have to think about. For the most part, I don't see many teams using ultrasonic sensors in FRC. They're used a lot in Lego robotics because the fields are much smaller and you're not going to be running into other robots because it's only ever one robot on the field at a time because you're completing a particular challenge. So for the most part, it's not really an issue. So we're on the home stretch, only 9 minutes left, and we can get through the last one more section before we're all done here, and that's the section on gyroscopes.
How long's your intro?
What?
How long is your intro?
My intro?
Yeah, for you.
I don't understand. What are you talking about? Just shush. So I can finish this. Tyler's been asking questions. You've just been making random noises. They might be off topic, but at least they're questions.
Yeah.
Anyways, there are 4 commonly used types of gyroscopes in use in the world today. Each charged with the task of measuring an angular acceleration, which can be converted into an angle, which is normally what most people will use when they're using a gyroscope. This is often done in multiple directions. This, and like this.
X, Y, Z.
X, Y, Z.
I haven't done that yet.
And it's probably one of the most useful sensors that you'll come into contact with. And gyroscopes can give you a lot of decent information about your robot without a whole lot of expense.
Can you have GPS on your robot?
I mean, theoretically, yeah.
Like GPS navigation? Like,
If you can get it to work in a building, yeah.
Yes,
Okay.
it works in relativity.
turn left.
Anyways,
Your target.
as I mentioned previously, there are 4 commonly used types of gyroscopes that are available for use in applications around the world. For our purposes, the type that we use is known as a vibration gyroscope. Now, it's not necessarily the vibration that you might think of. It actually uses something called the piezoelectric effect, where certain minerals or crystals, if they are vibrated, they create an electric current. And if you apply an electric current to them, they vibrate.
That's a what type of crystals?
Ever heard of a quartz clock?
Yeah.
A quartz clock uses the piezoelectric effect.
So like that's why like those watches that it says 25 crystal.
Right. It's quartz, when applied with a certain amount of energy, will oscillate at a certain speed to create a clock timing that can be used to time a second hand.
Okay, how much electricity does it create when it vibrates?
A very small amount, not exceptionally
I was gonna
large.
say, global
So
energy.
if you take a quartz rock and you hook a positive and negative, it'll just start vibrating.
You won't notice the vibration. It's a lot. The larger the object, the amount of energy that you need to get it to vibrate goes up exponentially.
Is it
Tiny
because
rock and like
is it when
That's still too
giant
big.
cables.
Still too
is
big.
it because it makes the electrons move around? I mean the element.
Because of the I'm not entirely sure on that point. If I had to hazard a guess, it probably has something to do with the fact that there are such a small number of atoms in that general area, and they're all trying to share a huge number of electrons and get them moved on to the next location, that all that switching causes a bunch of vibration, because you're giving up a lot of energy at that point. as you change from energy level to energy level. So it makes a lot of vibrating and energy. Anyways, most gyroscopes you'll come across will allow you to communicate with them with I2C and RS-232 UART, but as with ultrasonic sensors, there are a wide variety of communication setups available for you. Most gyroscopes will come with at least 2 forms of communication on them. Okay? As with ultrasonic sensors, there are various things that can create interference with gyroscopes, and they need to be dealt with the best you can. The first thing is temperature. Obviously, when atoms heat up, they start to move around a little bit. So the
Energized?
yeah.
Oh yeah.
So the piezoelectric effect gets affected by temperature. So as the temperature goes up, the electrical conductivity of the substance starts to change a little bit. So it might vibrate more, it might vibrate less. My recommendation is don't buy a gyroscope without a built-in temperature sensor, which most of them do come with built-in temperature sensors and automatic compensation for changes in the temperature. We're almost done, Tyler, I promise.
How are you not an ice cube right now?
Because I'm used to it.
6-inch jacket.
The next thing is vibrations. Well, vibrations don't normally do as much damage as temperature might, or the next thing that we're about to talk about might. They can still cause problems. The best thing to do is just to make sure that your gyroscope is secured to the robot very well, and if you can, put rubber bumpers on where you put the screws. That way, you know, it takes some of the shockiness out of what's going on.
What are they cutting?
The final thing to worry about is electrical interference. Particularly magnetic interference from things like motors, where that electrical energy that's in a field around the motor can actually affect how the piezoelectric effect works to sense angle. So no, don't put them on your motors. It's usually good to keep gyroscopes a few inches away from your motors, simply because there's just so much noise in that general area that it's not really a good idea. It's also a good idea to keep it away from wires, at least bigger wires like the battery cable or the power for the motors and stuff, simply because when you move energy across a wire, it does create an electromagnetic field, and while it's much smaller than what a motor creates, it's still there, and with enough energy going through it, it could cause some disruptions. Now, the last thing for gyros is, unlike ultrasonic sensors, gyros usually have to be calibrated further rather than just the built-in calibration for temperature. This helps to reduce drift. Now, drift just means that over time, a gyroscope will start to accrue small amounts of error, and that error can start to affect your readings. Now, a good gyroscope, a solid one that you spent a little bit of money on, $40-50, will have a drift of about a degree every minute, at least when it comes to piezoelectric gyroscopes. Other types of gyroscopes might provide more accuracy and less drift, but they cost more. So that's basically it for today. We'll talk about, we have accelerometers, encoders, other sensors, and that's it before we're ready to start talking about programming specifically for robots. Now, before Justin leaves and runs off, before either of you leave, I am going to say a couple things to you guys before we run back over. So I'm going to stop this video